Alright, so this second video for Unit 2, Part 2 on lab stoichiometry is probably going to help make a little more sense of our baking soda lab, as well as in part the mole ratio lab that we're going to be talking about in class when we go to graph data. Some key terms, you've seen a lot of these already. Limiting reactant is the one that is used up completely, and it determines basically how much of your products you can make, while an excess reactant is the one that's left over. In order to determine how much product you actually formed, you have to find a way to try to get this reactant out of your mixture. The actual yield is what you made, what you generated. So in the baking soda lab, it would have been the amount of carbon dioxide. And then theoretical is what you would determine using stoichiometry if you were able to use all of the limiting reactant completely. Oftentimes, some of the limiting reactant might get lost through to transfers, or it just might not be consumed as completely as we think it is. And we can use percent yield to determine basically a ratio of that actual yield, the amount you made in lab, to theoretical yield. In lab, obviously, you'll have actual yields from your data. In a problem in class, you would have to be given actual yield information. So we're going to work through 3 examples, I believe. First one, we're going to look at the synthesis of mercury 2-bromide from its elements, mercury and bromine. And I want to know how much mercury 2-bromide I can make from 10 grams of mercury and 9 grams of bromine. With that in mind, I don't know which one of those reactants I'm going to consume first. So I have to do 2 stoichiometry problems. One where I take the grams of mercury and I figure out how much mercury bromide I can make. And then I do the same for the amount of bromine I was given. So I'm starting with the first reactant, 10 grams of mercury, and I'm going to set up a stoichiometry problem where I go from grams of mercury to grams of mercury 2-bromide. Molar masses with grams, so 200.59 for the mercury, 360.39 for the mercury 2-bromide. And then I need to look at my balanced equation to relate the substances to one another. They both have coefficients of 1, so we're good to go. The grams of mercury cancel out. I multiply across and divide. 10.0 has the fewest sig figs. It has 3. So when I did the math, I got 18.0 grams of mercury 2-bromide could be made if I had more than enough bromine to completely use up all of that mercury. Again, I have to do 2 stoichiometry problems with this because I need to figure out which reactant makes less mercury 2-bromide, because that's the one I'm going to run out of first. It's kind of like when you bake. If you run out of an ingredient, you can't make any more of what you're trying to produce. So if I start with the 9 grams of bromine and I go from grams of bromine to grams of mercury 2-bromide, the molar mass of bromine now goes in the denominator, 159.80. Mercury 2-bromide's molar mass goes in the numerator, and I relate the 2 substances to one another, again 1-to-1 ratio based on my balanced equation. So the grams of bromine cancel out. 3 sig figs are present in my 9.00 grams of bromine, so I want 3 sig figs in my answer. So although we had less bromine, because mercury weighed so much more and everything was in a 1-to-1 ratio, we actually made a smaller amount of mercury 2-bromide. From the 10 grams of mercury. So you can't just assume because you have a smaller amount of a reactant that that's the one that's going to make the smaller amount of product. You have to go through and do the mathematics. So based on this information, the one that we're going to run out of first is mercury. So mercury would be my limiting reactant. The one I will have left over when this is said and done is bromine. So that would be my excess reactant. And the amount of mercury 2-bromide I can actually make would be the 18.0. That would be my theoretical yield. That is the most mercury 2-bromide I should be able to produce if I mix these amounts of reactants together. So our second example is actually going to be a 3-part problem. We have lithium and aluminum chloride makes aluminum and lithium chloride. So this is a single replacement reaction. We are needing to balance this equation, so we'll do that in a second. We're given 45 grams of lithium and 300 grams of the aluminum chloride. Those seem like crazy amounts. And again, you might want to say, well, lithium's going to be limiting and that's all it's going to be. We need to go through and just double check. And then we're going to use those two to make a total of 55 grams of aluminum. that 55 grams isn't going to come in play initially. That's basically what you would have made in the lab. That's your experimental information that's giving you the yield of aluminum if you had completed this reaction in a laboratory setting. So just kind of put that 55 grams to the side for right now. We're going to just be focusing on the reactants, since the first question asks us to find the theoretical yield. And the theoretical yield always comes from your limiting reactant. So I'm going to balance this equation so I can go ahead and do stoichiometry to figure out which product is going to make this, or excuse me, which reactant is going to make the smaller amount of product. I have one lithium on both sides to begin with, so that's good. I have one aluminum on both sides, so that's good. But I only have 3 chlorines on the reactant side while I have 1 on the products. So that means I need 3 lithium chlorides. As a result, I now need 3 lithiums on the reactant side. So this should be balanced now. Because I have 2 products, I can pick either product to find the yield of. Whichever reactant is limiting, it will make the smaller amount of those 2 products. Because I was given information about aluminum, and frankly aluminum's mass is easier to determine than lithium chloride, I'm going to take the grams of lithium and figure out how many grams of aluminum I can make. And then I'm going to take the grams of aluminum chloride I was given and figure out how many grams of aluminum I can make from there as well. So I started with my 45 grams of lithium, and I got rid of the grams of lithium to go to grams of aluminum. Both are elements, so I can find them on the periodic table. 6.94 for lithium, 26.98 for aluminum. I look at the balanced equation and I see that it is a 3-to-1 ratio between lithium and aluminum. So 3 goes with the lithium, 1 goes with the aluminum. The grams of lithium cancel out. I have 3 sig figs in the 45.0 grams and the 6.94 grams, so I want 3 in my answer. So from 45 grams of lithium, in theory, I can make 58.3 grams of aluminum. Is that the smallest amount? I don't know yet. I'm going to figure out by taking the 300 grams of aluminum chloride and figuring out how many grams of aluminum I can make from that amount of aluminum chloride. I'm starting with grams of aluminum chloride, so they go on the bottom. I want to find grams of aluminum, so they go in the numerator. Molar mass goes for both aluminum and aluminum chloride. 133.33 is what I got for 1 Al and 3 chlorines. 26.98 from the periodic table. According to my balanced equation, it's a 1-to-1 ratio between the two. So when I multiply and divide, the 26.98 has the fewest sig figs this time, along with the 300.0 grams. So I want 4 in my answer. I should have given you 4. Sorry about that. However, it's not going to make too much of a difference, because even though we had so much aluminum chloride to start with, the difference between the grams of aluminum made were actually pretty close. But lithium made slightly a smaller amount of aluminum than aluminum chloride did. So the limiting reactant would be lithium, while the excess reactant by just a tiny amount would be the aluminum chloride. My theoretical yield is based on that limiting reactant, which is why I'm not going to worry so much about the 4th sig fig with the 60.7 grams of aluminum, because my theoretical yield is going to be based on that limiting reactant lithium, 58.3. So I won't need to use that second stoichiometry problem for anything else right now, other than identifying what my excess reactant is. Part B asks us to calculate the percent yield. Percent yield, if we review, is actual over theoretical. You may remember that I told you actual comes from data collected in lab, but in a problem like this I would have to give you that information. And so that's why back at the problem that we started with, I told you how much aluminum was made, 55 grams. Right? You have to be given that. I can't ask you to solve a problem like this without giving you some information to find theoretical yield and giving you a percent yield, but I have to give you 2 of those 3. So I've told you what the actual yield is, 55 grams, and you've already calculated the theoretical yield back in part A, 58.3 grams. We multiply that by 100, and when we do that proportion, we get 94.3% yield was made in this lab. That of the 55 grams that were made, we were able to collect 94.3% of what we could have. So this is a pretty good percent yield for this experiment. The last part, you really want to make sure you pay attention to the different steps. It's going to be the same problem, But rather than taking the theoretical yield or finding the limiting or excess reactant, we're going to figure out quantitatively how much of that excess reactant we had left. If you started with a certain amount of the excess reactant and you used up some to use all the limiting reactant completely, you know how much you have remaining by taking the difference between those. So the mass of the excess reactant is the difference between the initial mass of the excess reactant and the mass of the excess reactant used. We know what the initial amount was. We were given that to start with. So we need to figure out how much of that excess reactant was used, and we can do that by using all the limiting reactant to determine the amount of excess reactant that was needed. So we're going to do one final stoichiometry problem where we take the grams of our limiting reactant and we convert to the grams of our excess reactant. Because with stoichiometry, we should always be able to figure out how much of each of the reactants and products were needed or were produced in that equation. So if we're starting with the 45 grams of lithium and we want to use it completely, we want to go to grams of aluminum chloride, our excess reactant. Grams get smaller mass. We've already done both of those. And we look at our balanced equation and we see it's in a 3-to-1 ratio between lithium and aluminum chloride. The grams of lithium cancel. I have 3 sig figs in the 45.0 as well as in the 6.94 grams. So I want 3 in my answer. And that tells me that I needed 288 grams of aluminum chloride to completely use up the 45 grams of lithium. To get how much remained of that excess reactant, I take the difference. I subtract from 300 grams my initial amount, the amount I used, the 288. The subtraction, we look at decimal places. We have no decimal places in 288, so when I do my final calculation, I want none in my answer. Sorry about that. And I got 12 grams of aluminum chloride remained. All right, so that should give you enough information to be able to work the problems in class involving lab stoichiometry.